I see. So we still have a few minutes, right?
Yes, yes. We have 4 more minutes.
Good. I see. So we still have a few minutes, right?
Yes, yes. We have 4 more minutes.
Good. I see. So we still have a few minutes, right?
Yes, yes. We have 4 more minutes.
We'll start sharply.
It seems to be an endless loop at the moment.
At least we can start now.
Okay.
Very good.
So good evening, everyone. I'm very happy to welcome Professor Hartmut Monien from University of Bonn. Actually, my pronunciation may not be correct. Please correct me.
No, Bonn was perfect.
So thank you so much. He is today giving talk on actually, again, the first portion I don't know how to read, and the modular curves associated to sporadic group CO3 and J2.
Very good.
So, okay, so sorry. So thank you so much. So I again welcomes. Sir, you can start.
Very good. So thank you. Today it will be a little bit faster and a little bit more compressed than last time, and we will apply more than I showed you last time. So I start again with this theorem by Kai Magar. who had a very nice theorem about sporadic finite simple groups, saying that X, so I also will repeat some of the stuff I said last time so that you can actually connect it now. So X is a compact connected Riemann surface, phi is a non-constant meromorphic function X, monodromy is the monodromy group of the cover X to the projective line. And the theorem by Kai Margaret says that let G denote a finite simple group. And so I stated this already. So the question now in today's talk will be, how to actually calculate this function phi for the two groups J2 and Conway 3. Why only J2 and Conway 3? Because the cover was already calculated for the other sporadic groups, and J2 and Conway 3 were the last two which were missing for nearly 30 years, where people were trying to do that. So, and Belly's theorem should be also noted, which answers the question which Riemann surfaces can be defined over algebraic closure of Q bar of Q. And the answer of Belly is only those which admit a Belly map. And the theorem is saying that any non-singular algebraic curve over C represents a compact Riemann surface which is ramified, which is a ramified covering of the Riemann sphere, ramified only at 3 points. So and these 3 points can be taken to be 0, 1, and infinity, and the rational map is known up to coefficients. So let me give you a worked example, which I didn't do last time. So here's a worked example where one actually does the calculation for a relatively simple case, which is the congruent subgroup gamma 04 of PSL to Z, given by two matrices with integer entries, A, B, C, D, such that C is 0 mod 4. It acts transitively on the upper half plane via Möbius transformation. It has index 6 in PSL to Z, and it has a compact Riemann surface of genus 0. So this Riemann surface X gamma 04 corresponds to a 6-fold cover of the sphere. Now, as I explained last time, it is relatively easy to calculate explicitly that curve. Here's the Riemann surface. So this is X gamma 04 with the sides, the left side and the right side glued together, and the magenta line, the blue lines glued together. So this is a genus 0 Riemann surface. Now, when you look at the tessellation with the cosets, you actually see that it has index 6, as we explained last time. It's not so hard to calculate now. And this is the Steadicam tessellation, where you can actually see, the copies of the fundamental domain of SL to Z, and the elliptic points, the red ones, the elliptic points of order 3, and the green ones, the elliptic points of order 2. You can actually see the copies of the elliptic points of the original fundamental domain in this cover. Now, as you can see, there are these 2 points have to be identified because these two sides are glued to each other. And again, these 2 points have to be identified. So there's only 1 point here, and there's only 1 point here. So we have actually 3 elliptic points of order 2 and 2 elliptic points of order 3. And that information is enough to write down, number 1, the design, and then also the algebraic equation for the cover. So what I'm using here is basically that I have 2 elliptic points of order 3. So this is this part. Then I have 3 elliptic points of order 2. This is this equation here. So elliptic points of order 2, and here elliptic points of order 3. And then we have to talk about the cusp. We have one cusp of with 1 and one cusp of with 4. So this is enough. So this picture we just looked at contains enough information to basically write down these algebraic equations immediately by just writing down these rational functions with the corresponding number of elliptic points of order 3 and elliptic points of order 2, and the cusps. And the equality follows from the fact, that these two covers have to be identical and have to be exactly 0 at the elliptic points of order 3. Now, when I just write down the algebraic equations for the unknown coefficients x1, x2, x3, and so on, we find this algebraic set of equations, and this algebraic set of equations is small enough that it can actually be solved explicitly, and you can do that in any system you like. So any computer algebra system which you like, actually does that. In principle, it's of course helpful to reduce to a Gründner basis. In this case, these equations are so simple that they can be solved easily in any way you want. Now, there are two solutions, in fact, of that system. One has one for which x1 has the value 256, x2 4096, x3 16, x4 minus 480, and so on. So you can write down these functions which give you the splitting of the which give you the elliptic points of order 3 and elliptic points of order 2 here, and also for the cusp. So that is in fact the belly map which one was looking for, because this function f of z is identical if one plugs in the Hauptmodul for this subgroup gamma 04 into z. This function again gives you the Hauptmodul of the full modular group. And the second solution, in fact, does not, and that's enough to exclude the second solution. So the first solution is basically the desired belly map. Now, once you have that, you can check, that you write down the Hauptmodul for gamma 04, and you can express that as the quotient of eta functions, and with the Q expansion here. And when you plug that Q expansion into the rational function f, you actually see that you obtain the full modular function of the full modular group with this rational function. And that is basically the defining property for the, so you have found the cover. So the calculation basically amounts to solving this algebraic set of equations. And once you have solved these algebraic equations, you have the belly map, the rational map from one Riemann surface to the other. Because J gamma uniformizes the fundamental domain of gamma 04, and J uniformizes the fundamental domain of the full modular group, and F is just a rational map which maps one to the other. So that's for gamma 04, which is a congruence subgroup, which is simple enough that one can solve actually these algebraic equations. Now, in the end, what we will do is have solve these algebraic equation for a belly map where the number of unknown coefficients in this rational functions is enormous, because the degree of the polynomial in the numerator will be 276. So what we have is, in the end, for the belly map of Conway 3, for example, we will have an algebraic system of equation which in 276 variables of degree 276, and we have to solve this algebraic set of equations exactly. So that is, for a numerical analyst, this is an impossible task, and one has to find a way of simplifying that to even be able to study this algebraic set of equation. If you look, for example, if you look at solving these algebraic, yes?
May I ask why did you choose gamma 04 rather than just gamma 2?
Well, gamma 04 is a little bit more complicated than gamma 2.
So gamma 2 is more complicated.
Well, in some ways, it's infinity, infinity, infinity. So it just doesn't have, it has its own quirks. But I mean, it's just an example. Don't worry about it. I mean, there's no deep reason.
There are no elliptic points there.
Yeah, that's right. We will look at different examples, but I mean, you know, this is one example where one can do everything explicitly. Gamma 2, one can also do everything explicitly. So I mean, this, you know, what I'm saying is, if you want to solve these algebraic equations explicitly, it is in this case a doable task, and you know, any method will work. And the Gröbner-based methods, you know, they are basically double exponential in the number of variables, and that means that for 276, I mean, it will not work at all. I mean, there's no way, I mean, that you could solve these equations, I mean, in degree 276. Even 24 is already an enormous task with Gröbner bases. So now I would like to show you, before we start really, I mean, the calculation is, I would like to explain to you again what I said last time, what I mean by reduction to elementary cusp. And then I would like to explain the difference between congruence and a non-congruence group. So if gamma is any finite index subgroup of PSL to Z or SL to Z, then we can find for a rational number H over K, we can find a matrix rho by solving a congruence, which is H times H prime equals to minus 1 mod K. This matrix has determinant 1, and it sends H over K, H divided by K, to infinity. So then, I mean, as by the definition of a coset, we know that there's exactly one gamma amongst the coset representatives of gamma, for which T, which is defined as gamma to the minus 1 times rho, is element in gamma. That means that T maps H over K to a Ferri fraction in the fundamental domain, because that's, I mean, what the coset representatives give you. So then, I mean, the fundamental domain might contain a number of cusps which are equivalent. So then you can, you know, map it again, I mean, by using the pairing matrices to the smallest one of these cusps. And then you have found a unique cusp which corresponds to H over K. And the operation count for this is basically the index of gamma. Right, because you have to find the matrix which gamma to the minus 1, which I mean is in the coset. So once you do that, then you can look at the difference between congruence and non-congruent subgroups. So what I'm doing here is the funny thing, I'm giving you only the permutations, and from these permutations, with using the Ferri symbols, as I explained last time, you can deduce almost all properties of the corresponding modular group. So if you take this, these two permutations, you can see that the Riemann surface has genus 1, which corresponds to the subgroup, which is defined by these two permutations. It has a generalized level of 24. It has index 48, and it has 8 cusps. So that means no, we just have 8 cusps. Now, as a similar example, I take a non-congruent subgroup. You cannot actually see from the permutations directly if this is a congruent subgroup or not, which is this explicit example. So I give you 2 permutations, and these 2 permutations again generate a transitive permutation group, and you can again do the sum homomorphisms to the modular group, and then you see that this non-congruent subgroup has genus 0, generalized level 24, so the level is the same as before, and then index 18, and it has 5 cusps. Now what I'm going to do is something funny, I mean, which is just look at the following. So what I will do is I give you a plot where I take the integer numbers 1, 2, 3, 4, 4, 5, and so on, 1, 2, 3, 4, 5, and so on. P will be the numerator and Q will be the denominator of the number in the square. So here we have the fractions, I mean, which are, 4 over 4 is of course 1, 3 over 3 is of course 1, but you have fractions or cusps, I mean, in this elements of Q in these squares. So what I will do is I will take this number 4 over 3, for example, reduce it to the cusp, the elementary cusp in the way I just described. And I will color code the cusp classes. I mean, instead of numbers, I will just give it a color. And I will color the squares according to this cusp class. So now if I do that for the congruent subgroup, I get a regular picture like this. It looks like a carpet, very regular. Now, in the other case, I get a picture like this, which looks more or less completely random. So I wanted to explain this again, I mean, so that you can actually see, I mean, this difference between congruent and non-congruent subgroups. So as we said before, I mean, the sporadic groups can be represented as quotients of the full modular group with non-congruent subgroups, and very little is known about the modular forms of non-congruent subgroups. And Hacker operators are not applicable because the commensurator basically is 0. And that means you cannot actually define Hacker operators in the same way you do for the congruent subgroups. And there's no simple way to determine the Fourier expansion of a Hartmut module of a given non-congruent subgroup. So there is where these ferry symbols, which I explained last time, come into play. And here I say again what the homomorphism is. And again, I mean, these are the ferry symbols. And the one thing I wanted to show here today is a comparison of implementations. I mentioned that last time, but I didn't give you any figures. So here, I mean, these are all congruent subgroups. And for congruent subgroups, I mean, as I explained last time, you have basically linear relations. And that means you could use an ON algorithm to determine the generators and the cosets. But if you do it, I mean, with this ferry symbol, with using the ferry symbol, then, I mean, it's still an ON squared algorithm. But I just wanted to show you, I mean, that in magma, even for gamma 8 takes a sizable time. And then if you take gamma 16, it takes a long time. And then for gamma 32, it fails. And if you do the same thing for gap, which is again implemented by Helena Vera, I mean, you use a long time, I mean, with the ferry symbols in gap, I mean, to determine the generators of gamma 32. And in Sage, I mean, it's just a minute. So, I mean, that's one thing I wanted to advertise for Sage. Now, this example I showed already last time, which is the example M24. And here it's, again, I mean, just done explicitly so that you remember. You have basically all the information, including the fundamental domain, the design, and the ferry symbols, and the generators, which is enough information to actually obtain the rational function, I mean, the belly map, directly in Sage. Now, let me explain to you how I did this calculation or how you could do this calculation for any group, any subgroup of PSL2Z and SL2Z using analytic number theory. So this is not what I'm going to use in the end, but it's useful to know. So the starting point, which I want to explain to you, is this paper by Rademacher on Fourier coefficients of the modular invariant J by Rademacher in 1938. And the main idea there is basically, if you want to know the Fourier coefficients, then, well, you do a Fourier integral. And the Fourier integral is over a contour C, parallel to the real axis, just above the real axis. And that Fourier, and this line on which you do the Fourier transform you can split into intervals by using rational numbers. And what you do then is, instead of integrating along a line parallel to the real axis, you convert that integral to an integral over Ferri arcs of order n of the circle C with the radius exponential of minus 2 pi over n squared. And then the sum runs over h and k with h over, where these are two coprime. Now, why is that useful? Well, you can convert this Fourier integral into a sum, and you basically can simplify that integral by understanding that your Fourier coefficients is dominated by the contribution of your function in the range by the contribution of the function at 1 over q by the cusp at infinity. So this function f here, which is the Hauptmodul which we are going to calculate, can be estimated in these Ferri arcs, basically by this contribution 1 over q. Now, going through the details, I'm not going to go through all the details of the calculation, but basically, what you can do is, by summing over these Ferri arcs and integrating over this range, you can simplify this integral. And the integral can be basically understood as a Bessel function, a modified Bessel function. And once you have that, you are left with this sum. So this sum, for a congruence subgroup, this is all easy, and this AKN can be calculated directly for a congruence subgroup. So here in this case, it's just H mod K. And so you have an explicit representation of the Cn in terms of, a Klostermann sum. Now, this, may sound only theoretical valuable, but as Rademacher showed in this very early paper, this sum actually, converges relatively quickly to an estimate for the Fourier coefficients. Now, this work was extended by Zuckerman, and there's a 1938 paper on the coefficients of certain modular forms, which I think nobody much looked at, for non-congruent subgroups, but you can actually generalize that. And in fact, what Zuckerman did, is sufficient for any modular group. You basically have to do this sum over the Ferri arcs a little bit more careful. So the basic input for the calculation are the principal parts of the cusp, and the main difference to the work of Rademacher is that for the subgroup gamma of PSL to Z, the pullback to a cusp representative is required. And that's what I just showed you how to calculate. You remember, that this algorithm, where one puts the rational number h over k to infinity, and then reduces it back to the fundamental domain, and then you find the corresponding cusp representative. That's enough for this algorithm, which I just explained, to generalize it to non-congruent subgroups. So what you do is you expand at each cusp. So you have at a cusp x, you have the J function expanded into, you do a Q expansion in this particular form, where basically W is the width of the cusp. And then at every cusp, we have the expansion from 0 to infinity. So except at one cusp, which you have to choose as the singularity. So one cusp, it has a 1 over q expansion, a 1 over q leading term, which is the dominant expansion coefficient, which gives you this Klostermann sum. So, for example, if you just take a congruent subgroup, which everybody knows how to deal with, let's take gamma 0, 32. This is the fundamental domain of gamma 0, 32. And what I'm showing you here in this plot is basically the radius of convergence of a cusp expansion with a particular cutoff delta. So in each of these circles, you can obtain an estimate of the J function of the Hauptmodul with a given accuracy. And so, I mean, this is the accuracy 41 digits, I mean, which I choose for no good reason in this example. So what you basically do, I mean, when you calculate the Fourier coefficients, what you do is analytic continuation from one cusp to another cusp by this overlapping regions. And that's what I tried to explain last time in this story about the uniformization of the circle plus the rectangle. So what you have now is an expansion which has a region of overlap, and that region of overlap can be used to use later the uniformization algorithm of Schwarz. But now, let me just apply what I said before about these Ferri symbols. So with these Klostermann sums, you can calculate, for example, for gamma 03, you can calculate the Klostermann sum with the largest denominator up to 128, and what you obtain is an approximation for the Hauptmodul with these coefficients, so 53.995, which is an approximation to 54 apparently, and then you get as the quadratic coefficient, you get 76 plus a small deviation. So then the Klostermann sum is still not the final value, but I mean, you get some approximation, and that's enough to identify the first few terms. And in fact, I mean, that's enough to determine the belly function here. And this can be applied also to non-congruent subgroup, because basically all you need is the identification of this cusp at h over k when you do this integration over the Ferri arcs. Now, this is yet another method which I'm going to explain. So what are these methods trying to achieve? What we are trying to do is to characterize the meromorphic function J gamma in the upper half plane by some kind of series expansion at all cusps. And Hedgehog, I mean, basically does a random transformation depending on height and radius of conversion of the Q series do not necessarily overlap. Rademacher and Zuckerlin, I mean, you can use a generalized Klostermann sum with very slow convergence. You could use other series. I mean, if you have, for example, a compact Riemann surface. And for that, I mean, you better look at the next talk. But what I'm reducing it to is basically a very simple idea. All these methods are attempting to find a solution of two partial differential equations, one for the real and one for the imaginary part of the Hauptmodul J gamma of the corresponding group. So we have the real and imaginary part of this J function, and both obey a differential equation. So analyticity means not only that the function is smooth in the region of analyticity, but it also means it obeys the differential equation. And that point is, I think, somehow lost, has been lost in history, that analyticity really means differential equation. And the boundary conditions, of course, I mean, is at infinity is that the J function, I mean, of the corresponding group has to go like 1 over Q plus the constant, which is always a modular function for any group, plus some Q expansion. And the complicated part, which is now left, is basically how to incorporate the boundary conditions in the solution. So this constant for uniqueness, I mean, if you really want to have a unique solution of this differential equation, what you do is you set this constant to 0. You fix that constant. Then everything is fixed because boundary conditions will be fixed and and you can solve the differential equation. So what you have is a partial differential equation with periodic boundary conditions. So this gamma 1 corresponds to a mapping from these two sides, from the magenta side to the magenta side. And gamma 2 corresponds to an elliptic point of order 3. And I mean, you map these two sides to each other. Again, you have periodic boundary conditions. And here you have periodic boundary conditions. And now what I'm going to do to solve that, I mean, for example, I mean, it's not necessary. I mean, that's one of the methods I have been using, is you triangulate that fundamental domain. Now, what you get then is you can solve this at least approximately this partial differential equation by expanding in these triangles in some basis set. And that's a technique which is very well known to applied mathematicians. This is used, for example, in calculating, I mean, the wing, the flow around the wing of an airplane. This is a trivial thing for a numerical analyst. Basically, what you do is a finite element method, and you try to minimize some norm some Sobolev norm for solving this this partial differential equation on these triangles. So each nodes of these triangles basically specifies this. Each triangle has some linear coefficients for these basis function, and then you basically have to patch these basis function from one triangle to the next, and then basically that's giving you the solution of the partial differential equation. The solution of the partial differential equation is not itself interesting.
Anything particular here about the chosen triangulation, or just any triangulation?
Well, I mean, you have to choose it according to the gradients, I mean, which you have in the function. So I mean, you have to do an adaptive sort of meshing. So down at the cusp, I mean, you need more triangles to characterize your function better.
But it will depend. Your calculations will depend on the triangulation, right? So there's nothing canonical about it.
No, but you can choose. I mean, according to the accuracy you desired, you can choose the triangulation.
I see.
And I mean, you can basically, do an adaptive grid, and I mean, people are very, very well used to that in applied mathematics. So I mean, you can use various methods. I mean, various packages to solve this partial differential equation, but basically, no big deal, except for the periodic boundary conditions, which are tricky. I mean, too, because engineers are not used to periodic boundary conditions usually. So now, the point, I mean, which I made about the solution not being particularly interesting is that the only things you need to know is the special points of the fundamental domain. So here I marked the elliptic points of order 3, and these elliptic points of order 3, you can have, once you solve the partial differential equation, you have an approximation for the Hauptmodul at these points. Okay, and the point here is that I'm solving a linear equation. Remember, I mean, we started with an algebraic equation which is highly nonlinear and has many solutions by choosing the normalization that the Hauptmodul has to go like 1 over q at the cusp at infinity, and the constant coefficient be 0. I have defined boundary conditions for this problem, which give a unique solution to the Laplace equation on this fundamental domain. So there's a unique solution. So I converted this highly nonlinear, complicated problem into a linear problem, which I can solve approximately. So now, once you have this approximate solution, in the example I showed you before, I mean gamma 04, what you can approximate now is the coefficients x2, x1, x0 by the solutions by the numerical solutions of your differential equation. This is the evil part of my work. I used numerics to obtain an approximation for these points. And without the partial differential equation, you have no idea what the values at these points should be. So I used a linear problem to give you a starting point for an approximation for these coefficients. So up to now, everything is approximate. Now then, what you do is you take a Newton solver and solve the algebraic equations by calculating the Jacobian of your algebraic equation and linearize that. So you get a linear equation again, and you solve that to get a better approximation. And that is basically the Newton algorithm for the algebraic equations. And once you have solved these algebraic equations to high enough accuracy, you can identify the numbers as algebraic numbers. And once you have calculated the algebraic numbers as rational numbers or as integer numbers over a given number field, you can plug that into the equation and check that your solution actually is correct. So in this particular case, I mean, this gives you very quickly the solution. And look at this Q expansion at cusp infinity of this Hauptmodul for N24. With a Klostermann sum, I mean, when you include already 1,000,000 terms, I mean, you get an accuracy of 5% for the first coefficient A1. And you would have never guessed this Fourier coefficient A1 to have that exact form. So this is after solving the algebraic equation to a high enough accuracy and then identifying these algebraic numbers. And again, I mean, if you look at the calculation here in Sage, I mean, the total calculation took 15 seconds to calculate these algebraic numbers over this number field. And once you have calculated it to a high enough accuracy, I mean, then you basically are set. That's all you need to know. Now, for more general triangle groups, you can play a similar game. I mean, you have to work over a number field to get these more complicated general triangle groups. But you can, for example, compare that to a method by Elkies. So if you use p-adic methods, I mean, they calculated the belly map for M23, I mean, which took with the p-adic methods several CPU days for the initial search. So what you do is, I mean, you basically have to find a solution over a finite field of the algebraic equations. And there's no other way than to try all the numbers. That means, so if you have, for example, an equation of degree 276, you have to try these 276 numbers for each value in your value in the finite field. So, for example, if you take a finite field over 17, over the prime 17, you would have to, and you have 276 variables. That means you have to specify 276 variables in F17, and that is 17 to the 276 possibilities. And if you have all the calculators, all the computers on Earth, I mean, it will take longer than the age of the universe up to now. And probably longer than the universe will last, but who knows? Okay, and with our method, I mean, which is not p-adic, I mean, which just, I mean, uses these algebraic, these analytic approximations to these algebraic numbers, you can identify the same numbers in approximately 10 minutes on a laptop. So that's, I mean, the power of these analytic methods. I mean, so analyticity is not just, I mean, a statement that nothing actually happens with your function in a given surrounding, but it actually means something more stronger. Analyticity is really a powerful tool, in my view. Good. Now, I think I'm speaking too fast, but maybe I'm finishing too early today. So let me talk about Yanko2. Yanko2 is a group, I mean, which, as I said, can be defined by a tuple of two permutations of 100 objects, and it has some geometric meaning in the Leech lattice. So these two permutations over of 100 objects give you another permutation. I mean, if you take as sigma 0 times sigma 1 to the -1, you get the permutation sigma infinity, and you can see, I mean, that sigma 0 is order 2, sigma 1 is order 3, and then the last one is order 7. So this is a representation of Yanko2 as a 2-3-7 group, and that basically says, I mean, you can represent it as a modular group, either as a triangular group over a 2-3-7 of a 2-3-7 triangular group, or as a modular group, I mean, where you basically have this mapping of these sigma 0 and sigma 1 to sigma and basically sigma, sigma 0 is basically the inversion, and sigma 1 is inversion times translation to the -1. And using these analytic methods, I was able to show one thing, I mean, which is basically, this is the fundamental domain of Yanko2.
All the cusp fields are the same.
Okay, I mean, we have 14 cusps of width 7.
Okay.
And 2 cusps of width 1. No elliptic point of order 2 and 4 elliptic points of order 3. And
any explanation why the cusp fields are the same? That must be some group theoretic.
There's a group theoretic point, but I mean, I'm not familiar with that. So I mean, this is just the fact of life for me at this point. And it's a Horwitz group, I mean, because it's a 2-3-7 group, but and you can check, I mean, all of this, but the main point which you should keep in mind is this 2 cusps of width 1. And what I'm going to do is, I mean, I will choose one of these 2 cusps at infinity, of width 1 at infinity, to be at infinity. All right. So then, I mean, when you calculate, I mean, you actually can prove, I mean, with these methods I just showed you, that there's you can actually construct these polynomials, P3 and PC and P2 and PC, and you can download them from this archive if you wish to look at them. I wasn't able to fit them on the screen in any way. I tried. I cannot show you these polynomials. But you can find them as data in this archive paper. You can download the data, I mean, from this paper so that you can look at these polynomials yourself. But the main point is that the polynomials are defined over a number field of degree 10. Okay, and this number field, I mean, is a relatively generic number field, but it has a Galois group, which is the Rieth product of S2 and S5. So what is known for Yanko2 is that from calculations by Malle and Matzat, is that the upper bound for the field of definition of Yanko2 is actually 10. And you can actually reduce it because what you see here is sigma 2, is S2 wreath S5. And that tells you that this number field has a subfield of degree 5. The number field of degree 10 has a subfield of degree 5. And that gives you a quadratic equation over this field of degree 5. And the number 2, I mean this of the S2, actually comes from the fact that we have two elliptic points, two cusps of width 1. We have chosen one of these cusps to be at infinity, and we break the symmetry between these 2 points. These two cusps of width 1 are equivalent up to now in the group theory. And now by putting one at infinity, we have broken the symmetry between the two, and that introduces this Galois group S2 wreath S5. So the field of definition is actually S5, and in principle, one should be able to reduce the field of definition of this belly map to 5. I've not been able to do that, but I show you, I mean, that for the more complicated example for Conway 3, one can actually do that. And there's a particular reason for that, and I'll show you what that is. So, as I mentioned in my last talk, the group Conway 3 can be defined as a permutation group of 276 objects. And in the Leech lattice, this corresponds to pairs of 276 lines, which are stabilized by Conway 3 in the Leech lattice. And that corresponds to non-congruence group gamma of index 276 with no elliptic points of order 3, 12 elliptic points of order 2, 39 cusps of width 7, and 3 cusps of width 1. So this is probably not the largest belly map anybody has ever calculated, but I think it's one of the more complicated ones I have seen. So the point you should take away from this slide is that there are 3 cusps of width 1. So what I will do, again, I mean, I will expand around the cusp at the cusp at infinity, and I will choose one of these 3 cusps with width 1 at infinity. So what I expect from my previous experience is that the Galois group of the field of definition of my belly map will be a wreath product of S3 with some other group, which is more or less generic. Okay. And now when you look at it, then you can, once you do the explicit calculation, and again, I mean, you can get the data from the archive, where I have put the data for P3, PC, and P2. You can check, I mean, that actually these polynomials define a belly map. And this belly map corresponds to Conway 3. And the field of definition is actually an extremely large field. So what I have here is a degree 36 field as a field of definition of my belly map. So the polynomials P3, P2, and PC are defined over that field. And when you look at the field, you see that the Galois group of that particular field, and I should have written the letter L here, is S3 wreath at A12. And what that tells you again, I mean, that it must be possible to define that belly map over a smaller field of degree 12. And in this particular case, I was actually able to do that. So the first observation is that this number field contains a subfield of degree 12. And there will be a cubic polynomial over this degree 12 field, which defines the extension here. So remember the subgroup gamma has 3 cusps of width 1. So the structure of the Galois group, as I said, implies that L is a cubic extension of a field K with degree 12 with a defining polynomial. And here I've written down the smallest defining polynomial, which I was able to find. So there's a degree 12 field with this irreducible polynomial. And there will be a cubic equation defining L. Now, if you take this cubic equation and let psi1, psi2, and psi3 be the roots of that cubic polynomial of the extension field over K, then these 3 roots define a unique Möbius transformation if I map psi1, psi2, psi3 to 0, 1, and infinity. A Möbius transformation is defined by 3 points, the mapping of 3 points in the complex plane. Now, if you take that Möbius transformation and apply that to the variable of your belly map, Z, then this Möbius transformation reduces the field of the modular curve to a degree 12 field K. So one can reduce this to the smallest possible field. And now A12 has no more symmetries, extra symmetries, which you could use, I mean, to reduce the number field. So this is the generic field, and A12 is the field of definition of that curve. So in my paper on the archive, you can actually download the degree 36 fields, the Möbius transformation, and the degree 12 curve. So this, I mean, again, I mean, let me emphasize what I've done here. I have solved explicitly 276 algebraic equation of degree 276 in 276 variables exactly. And if you have any other method which does that faster than what I did, let me know. So in some ways, I mean, you know, it's anticlimax in some ways. I mean, that, you know, all you can get is these belly maps, but I'm telling you, I mean, you know, if you want to identify any of the coefficients of the polynomials as an algebraic number, it takes about a week on a computer, on an average PC. So finding all of the coefficients, I mean, I had to use a cluster, and I was redistributing all the input from the approximate calculation on this cluster to identify all the algebraic numbers. Now let me just mark one point if you want to try this calculation yourself. I mean, you have to find the algebraic solution of that field to a precision of 1,000,000 binary digits. So what I've, you know, before finding the exact solution with these algebraic numbers, which you can actually use to prove that you had found the right belly map, is that the algebraic numbers have to be identified. I mean, solved. I mean, the system has to be solved to a precision which, you know, I have not seen in any other calculation up to now for algebraic numbers. And that took me about a year, I mean, to actually solve that system on our cluster. So this was a major calculation. Why did I look at Conway 3 and Yanko 2? Well, from the sporadic groups, I mean, these were the only two polynomials or modular curves which were not known. And so Yanko 2 and Conway, I mean, Yanko 2 is actually in this new edition of this book on inverse Galois theory by Malla and Mazza. So my curve already made it there, but my Conway 3, I got too late to have it in that edition, in the new edition. And that is, you know, one of the modular curves, which I think will be remembered somehow. And if you want to find the modular curve over Q, you would have to look at the extension field. And that means you have to, you know, find an extension field of this degree 276 polynomial. And I think that's, you know, so large, I mean, that I'm not going to try that. I mean, somebody else from the younger people might have an idea of how to go about, but I mean, I have no idea of how to obtain that. So I think at the moment, I have no idea of how to reduce this belly map to a belly map over Q in the end. So that, I mean, one actually has solved the inverse Galois problem for Conway 3 over the integer. So that's my conclusion for today. So what have I shown you? Well, analytic methods combined with lattice reduction algorithm yield a powerful technique for calculating modular functions for finite index subgroups of SL to Z. And calculating belly maps for large index subgroups is still technically challenging, but possible. I told you what the required effort is, but I mean, I think for you know, smaller groups, it might be much easier. And if you have a particular modular curve you would like to look at, I mean, it might be feasible if you tell me what you want to do. So then, I mean, you know, from the number theory side, I think, I mean, the most interesting curve is question is really, can one say more about the field of definition beforehand? Because that would reduce the calculation enormously. So that's one point where I would like to have more input. And the other point is that basically, as we all know, I mean, this field of definition of the modular curve is related to the mapping class group. And that is related to automorphisms of the Riemann surface by Dane twists. And for example, for Conway 3, I know that there are 12 generating tuples of Conway 3, which are 2, 3, 7, which are non-equivalent to each other, not conjugated to each other. And this number 12, I think, is exactly the number of which gives you the degree of the number field. But beyond that, I don't know. I mean, and, you know, what I would like to have before I'm retired is an algorithm which, given the number field, given the permutations, and choosing the cusp at infinity, would give you the number field of the curve. I think that must be possible. There's not more data than the permutations. So from group theory alone, one should be able to basically obtain the number field. And that's, you know, what I've given you is an interesting example to look at, or two interesting examples to look at. And if you can find any way of determining this number field based on more interesting methods, I mean, I think that would be thrilling to be. It would be really enormously interesting. And, you know, I can tell you that when I put my preprint on Yanko 2 on the net, 2 days later, I got an email by Sarah asking me if I understood the Galois group. of the number field, which defines the modular curve. So I mean, that was the interesting point, apparently, for him. So Sierra was still interested in exactly these questions, and I think it's an interesting question in general. So that's all I have to say for today. I mean, if you have more technical questions, I'm happy to answer. So thank you. Thank you for your attention.
Yeah. Let us thanks to the speaker.
Very, very impressive.
Very nice talk.
Well,
I have one question about computations.
yes, sure.
You have given a table in which you have shown that this gap is better than magma, and then sage is better than gap for these calculations. And now gap is actually a part of sage now, but
Yes.
still sage must be having some additional features because of which the computations become fast. So can you comment on that one? Means what are the additional things in sage available,
Right.
of which this becomes faster?
So the point is simply, I mean, where this calculation, I mean, is faster is where you use the analyticity and actually calculate the solution of the partial differential equation. So in the beginning, we used some package from a guy in Paris, I mean, named Hecht, which is called it's some FEM package, I mean, which I can show you to, I mean, send you a link to, which actually, I mean, allows you to implement periodic boundary conditions. So we use just what people use in industry or in applied mathematics to solve the partial differential equation. Now that works fine. I mean, if you do not go to a very large index.
Okay.
And the tricky part is when you go to a very large index, then it turns out that the zeros of the modular curve are so close, I mean, that you need very high accuracy, I mean, even for that starting point.
Yeah.
And what I then was using was basically the expansion at the different cusps. And exactly this method of overlapping domains. So I expand at one cusp, then use the information on one cusp to calculate at a different cusp. And the trick is then not to use directly the linear equations, which Hedgehog and other people do, but to use iterative methods for solving that linear equation.
Okay.
And these iterative methods, I mean, for linear systems, they work better than, I mean, just solving a linear equation, which is, an n-cubed process. So if you have n coefficients, I mean, then you basically have an n-cubed equation.
Yeah.
And that's very slow. And so the iterative methods work faster. And then what I'm using is so-called Krylov subspace methods, which are a trick which is used commonly in linear algebra nowadays to solve enormously large systems. And they work also, I mean, you can use that as an acceleration for these iterative linear solvers. And that works very quickly. And one of the people who is listening is my student, David Berghaus, who is very shy and not willing to show himself, I guess. But he is a master of these methods. And I mean, he is currently implementing some of that. So in Purple Sage, which is a branch of Sage which is used for these more advanced calculation, and we will make that at some point. We will make that a public package.
Yeah. So apart from the facilities available in Sage here, also to use modified methods in the calculations, then only time becomes very small. Yeah.
Yeah.
Thank you very much. Yes. Thank you.
So, I mean, the bottleneck, I mean, in the beginning is the solution of the Laplace equation. But once you have that, I mean, then, also, it's more or less, a little bit advanced numerical calculations, but it's not that hard, really.
Okay, yeah. Thank you.
So for the low index subgroups, people must have made these calculations. Low index is how low? Until
24 is already large.
Is large, I see.
So, I mean, you probably know the name Swonky, right? So Swonkin and Lando have written a book on graphs on surfaces.
Ah.
And, he's one of the people who was, into these belly maps very early. And when I sent him my calculation and asked if it is worthwhile for M24, I got an email back saying, how did you do that? Because of the 15 seconds. So if you do this M24 calculation with Grübner basis, I mean, you need a relatively large computer, a supercomputer, in fact, and it will take several days on that supercomputer. And what I showed you is, I mean, there's 15 seconds on a laptop. I mean, that's the difference between techniques. So in the end, I mean, the result which I have is not an approximation, it's an exact solution. Because once you identify the algebraic numbers, you can expand again, and you have the modular function to any accuracy you want. And I mean, the belly map is the belly map. I mean, once you have solved the algebraic equations and over the integers, I mean, you can check exactly, it's done, right? So if I hadn't told you, I mean, how to use analytic methods, I mean, you would be mystified of how to obtain a result like that. I think it's not possible with any other technique at the moment. So, and as I said, I mean, if you try to use p-adic techniques, I mean, the smallest prime which I was able to show, I mean, that this calculation works for Conway 3 is 17. And as I said, 17 to the 276 is a large number. If you want to try each of these numbers, which you need, I mean, you need to solve it over finite fields before you can use p-adic approximations, right? I didn't show you any of the p-adic methods, but I'm well aware of them, and I also know how to use them. I use them for smaller examples, but as I said, I mean, you need the starting point, and that's the tricky part.
They take more time also, that's you mentioned.
Say it again.
P-adic methods, they take more time also, that you mentioned.
Yeah.
As compared to analytic methods.
Yeah.
Yeah.
So, and I mean, I think, I mean, one of the more promising ideas would be to look at Hegner points and really understand, I mean, how to approximate the J function at the Hegner points p-adically. I think that would be, would help dramatically, I mean, to calculate belly maps. If I had any idea of how to calculate, a given Haupt module at the Hegner points, that's enough. Right. So, but that the Haupt module at the Hegner points is, again, I mean, living in a more complicated field, because that's the splitting field of the modular curve, which is defined over this large field already. So I don't know how to do that p-adically, but somebody might.
So if you know the number field on which the curve is defined, then you want smallest number field on which the curve is defined. That kind of problem also you mentioned, yeah.
Right.
But I mean, there is no way of right now to try the various possible subfields of that number field, and there is no way of that type.
No, I mean, at this point, we don't know. I mean, we have some bounds, I mean, from basically the mapping class group of the surface, but otherwise nothing is known.
Yeah. Okay.
Yeah, sorry, you have to rely on me at the moment.
Okay.
All right,
Yes.
good. So if there are no further questions.
I have a question. Sir, when you have calculating integral, whether you are using that interval arithmetic or usual, because there is every step there is a chance of having error in the computation. So Sage have
No, it's not essential that I'm using interval arithmetic. I mean, because the point is, in the end, I'm identifying the algebraic number. There's zero error there.
Okay. Okay, thank you.
And I mean, I could use, there are very good libraries for interval arithmetic or ball arithmetic. In this case, I mean, for example, there's a very nice library by Frederick Johansson, which is called ARB, ARB, I mean, which is, arbitrary precision arithmetic. And that could be used, I mean, for these calculations. I don't see, when I was starting it, I mean, ARB didn't exist. And so I was using MPFR.
Yes.
And that was good enough. I mean, and a variant which is called MPFC, which is for complex numbers. So that was good enough, I mean, for this calculation. But no, the point is you don't need interval arithmetic, because you're not starting from a particularly accurate point and then you're keeping track of the accuracy, and you're not allowed to lose accuracy. No, the point is, I mean, once you have identified the algebraic numbers, you're done. There's no error whatsoever. And so that's the main point. And
thank you, sir.
So, the proof then that this is the right Belly map, you do basically by plugging in the algebraic number in the algebraic equation and check that it's actually solving the algebraic equations. Right, and that contains all of the information about the cusp and the elliptic points and so on. So I mean, there's no, yeah.
Okay.
Good. So I hope I